In this video, we're going to look at yet another type of probability called continuous probability. We're going to look at how functions can be used to describe continuous random variables, and we're also going to look at the key questions that come up in relation to this area of study. For those who don't know me, my name is Chris Iannazoni. I used to work as an engineer for a defense company, and I've since left that to start a career in tutoring. I make these videos to help VCE students do the best they can in math methods. With that out of the way, let's get into it. Continuous probability looks at quantities that have no limit to their accuracy. The typical example here is things like lengths or distances. For example, if I were to measure a rope, I might be able to say it's approximately 1 meter long. But if I measure just a little bit more closely, I might say it's 1.02 meters long. If I zoom in even more, I might say it's 1.02579, etc. meters long. There's no limit to the amount of decimal places that you can go to be more accurate. By contrast, discrete probability is all about quantities that can only be specific values. The typical example here is rolling a 6-sided dice. You're only going to get the numbers 1 through 6. You're never going to, for instance, roll a 0.5 on a dice. But discrete is a topic for another time. This video is just going to focus on continuous. Continuous probability is modeled using what's known as probability density functions, or sometimes shortened to just PDFs. These can be literally any function that you've come across beforehand, but in the context of probability density functions, there's a few key rules that are worth covering. The first thing to be aware of is that PDF graphs are interpreted differently to regular function graphs. In this context, the x-axis is actually the quantity that we're after, not on the y-axis. The y-axis is actually covering the probability of any given event occurring. And more specifically, the area under the function is giving you the probability. In this example, we're told that the time taken to complete a task is modeled by f of x, where along the x-axis is going to be the time in hours, and the y-axis is going to be the corresponding likelihood of any given time occurring. The second thing to take note of is that the total area under the graph must be equal to 1. This is because PDFs model everything about the scenario, all the total probabilities. And what we know from previous areas of study is that all the probabilities in a given scenario have to add up to 1. Hence, the area under this graph has to add up to 1. The last thing to be aware of is that the function can never go below the x-axis. This is because probabilities can never be negative. And remember, area below the x-axis is considered negative. Sometimes you're going to be asked to prove that a function is a PDF. And to do this, we're just going to refer to the two criteria that we covered earlier. First, let's figure out if the function is entirely above the x-axis. That only takes a sketch to do. The next thing we're going to do is prove that the total area under the graph is equal to 1. And this we just do using our calculus knowledge, by just taking the integral over the valid domain. There's nothing too special here. We're just doing the definite integral of a function, just like you would do in calculus. We're going to get a final answer of 1. Both criteria have been met. Therefore, f of x is a PDF. This is a slight variant on the previous question. This time, we're given an unknown in our equation, and we're told to solve a value of that variable such that the function becomes a PDF. And to do this, we're just going to refer to the two criteria from before yet again. The main one here is that the area under the function must be equal to 1. So again, we're going to set up that definite integral, but this time equate it to 1. We're going to physically make sure that it equals 1. This is going to give us an equation with only one variable in it. All we have to do is rearrange for the variable to get it on its own, giving us a solution k equals 2. Technically, you should also check that the function is still above the x-axis, although this has never actually been an issue in a real exam. This is the final variant of this type of question, where the unknown is going to be in the domain rather than in the function itself. The steps are still going to be the same though. We're still going to find a definite integral over this given domain and equate it to 1. These questions tend to be CAS questions though, so all we're going to do is plug it into a solve and then solve the value. Another common question is to find the probability that x is between some interval. In this circumstance, all we're doing is finding the area under the curve over that interval, which in this case we're solving between x equals 2 and x equals 4. Hence, when we set up our definite integral, we're just going to do the definite integral from 2 to 4. Just a quick note on the inequalities here. This is perhaps the only area of study where the inclusive inequalities are identical to the exclusive inequalities. This is because when we're dealing with continuous probability, we don't have these immediate jumps between each value. The next number after 2 isn't 3. It's 2.000000 and a million zeros later, 1. For that reason, when you're dealing with continuous probability, inclusive inequalities are the same as exclusive inequalities. Sometimes you're asked to find an upper or a lower bound of a given probability. This is always solved by leaving that upper or lower bound as the unknown variable in your integral. In this example, our inequality is a greater than sign. That means that a is a lower bound, since we're only looking at values that are greater than a. This one here was slightly more challenging because it was a circular function. And the issue with circular functions when you do this kind of thing is that they often have infinite solutions. So, just like any other circular function, we can get over this issue by just restricting the domain. Remember, a is itself an x value. It's the lower bound of our interval. So it itself is also bounded by our given domain, which in this case is from 9 pi to 15 pi. So all we're going to do is restrict our domain from 9 pi to 15 pi. Conditional probability also applies to this area of study. Just like always, when we're doing conditional probability questions, we start by writing the conditional probability formula. And also like in other areas of study, usually we start by focusing on simplifying that numerator, which we can usually do by consulting a number line. All we're going to do is look for the intersection between the two different inequalities. And in this case, we can find out that our intersection is between 2 and 3. And then from there, we're just going to solve the numerator and denominator individually and then divide through at the end. Don't forget to use a division symbol here. It makes the simplification look a lot easier. If you found this video helpful and would like to see more, I actually have all sorts of additional resources available for free on my website. Just click the link in the description and you can access them here. And if you'd like my personal help, then consider signing up for the tutoring program. I offer the first 2 weeks free of charge so you can get a feel for whether or not this will be a good fit for you. Otherwise, I'll see you in the next video.